It is it is a pleasure for me to be here talking in this group. I have myself seen some of the talks and I've been following many of the developments of the community that are a part of this group. I am a senior lecturer in Sheffield Hallam University. So Sheffield, I hope you have heard of it. It's in the Peak District in the UK. We have two universities, University of Sheffield and Sheffield Hallam, and the two of them are pretty much having like a lot of efforts to. Well, Sheffield is a very well established university. Sheffield Hallam, and now is having increasing the research, and I am part of this new effort to bring more research to the university. So today I'm going to talk about movements on the inside, active control of internal representations in spiking neural networks and robots. So this work started just as a with my collaborator and student Ong Htid, which is in the chat, and Sarah Hamburg, which I don't know if it's in the chat. We started wondering about like the state of neuromorphic computing and how you don't see too much of population coding approaches being used at least towards commercial applications. So a lot of people rely a lot on the spiking and on the on essentially following traditional architectures that are feed forward or ANN architectures and trying to map them into spiking. So we started wondering about how can we use population coding approaches, and in particular, we are very interested in persistent representations in spiking neural networks. And the question is, how do we control them and make them uh, do something useful, at least in the field of robotics? And this was this was also about this time that we started working on this. I started reading the papers from Carl's collaborators and probably many of you about a particular this particular representations of particular dynamics and the existence of things separate from other things and from environment. And we got very excited about these ideas, and we started wondering if we can use some of these ideas and apply them to the representations themselves. So, uh, so I'm gonna more or less give an overview of what we have been thinking about. It's all a work in progress. Some of it is unpublished, so is is on yes, it's in progress. Um, and then we're gonna show. So we're gonna show a little bit of the theoretical ideas, and then some of the key applications that we have in mind and we are working towards. Okay, so as I said, like the modern neuromorphic chips and applications, even when you speak to manufacturers, they don't really consider the fact that the dynamics themselves of the network are supposed to perform some of computation. And even the presence of persistent states or states that have that persist over time and have are time independent somehow is almost seen as going contrary to the whole narrative of having a spike energy efficient computer because well you have to hold some firing rate there. Um, but nevertheless, the brain uses a lot of population coding, and it has been shown to encode very robustly important variables. And then in this population coding, what's interesting is that the individual neurons stop playing a role, and then or such an important role, and instead they act as a medium in which these persistent representations exist. Um, so we want to work towards trying to use these persistent representations in particular in the field of robotics, which I believe they are very much needed if we want to use actual spiking neural networks to control robots. Um, Combining these two ideas and the idea of this particular physics and the existence of things, um, and also combining some observations that people have about representations in the brain, like a representational drift, the fact that neurons themselves don't seem to be part of the same representation sometimes, and the representation moves. Um, we started wondering, and we actually were forced to wonder if the representations themselves have some sort of autonomy. And or in some sense, they behave like particles in the sense that the free energy principle states. So how would an autonomous representation look like? So I guess we will start with a substrate, which will have neurons connected to each other in a structured manner. And this substrate should allow some sort of pattern formation, which will allow this kind of representation to emerge. And also, the representation should have obviously a particular partition in the sense that it should have some internal, some external, and something like a Markov blanket, if uh, to some in some sense. So in some way, the representation themselves will be able to detect changes in this medium, neural medium, and move away or towards particular goals that are set, for example, by homeostatic drives. In addition, these representations should also be able or should also naturally interact with other representations, right? So if you have um, the best analogy to that is having intrusive thoughts or having some sort of phenomena that uh, suggest some interaction between different representations at multiple levels in the brain. But obviously the question is, how will this look like, and what does it mean for a representation to satisfy all these properties and to behave sort of autonomously? So let's explore that a little bit. So we start with a model, which is a spiking neural network model. And we're going to work towards a mean field representation that allow us to do some sort of analysis or to explore some of these ideas, and then go back to the spiking neural network model and use it to to create some applications. We model our neurons, at least for analysis purposes, as Poisson spiking neurons with a rate that is time dependent and depends on the connections from other neurons and some bias there. Each neuron is connected to the other neurons through a synaptic kernel, which is kept the same in the spiking and the mean field representations. And then each neuron has an activation function, which in this case represents the rate of the Poisson process. Um, uh, in the weak fluctuation regime, so when you have not a lot of fluctuations in the environment and the mean kind of represents the state of the network, we can represent this. It's a known result that you can model the changes in the synaptic activation as a low-pass filter, first order equation, plus some sort of integration that comes from the firing rate, plus the fluctuations, which will be small and will be uncorrelated in space and time. Um, so we are going to start from these mean field representations. In the following analysis, we're going to use actually the voltage version of these mean field representations, which essentially changes the nonlinearity and put it in the on the inside. Sorry, this is wrong. This shouldn't be here. But so you put the nonlinearity inside, and the rest is the same. So this will be our starting network. So it's a first order non-local kind of equations, and it has some again some fluctuations that we will talk about later. So the first thing that probably is interesting to do is to try to associate or try to find a connection between the theoretical underpinnings of active inference if we are to suggest that the representations are behaving like particles somehow, and somehow they are um, minimizing some sort of surprise about the environment. um, it is at least useful to try to find this the corresponding analogs to the particular partitions proposed by the in the active inference field. So we will start with a symmetric kernel, which depends only on the distance of the neurons, commonly known as the Mexican hat. This is necessary for the existence of the bumps. No, well, it's sufficient for the existence of the bumps. We will see that there is other kernels or other mechanisms that generate bumps later. And the reason this is is sufficient, at least for the existence of the bump, given some conditions that we will see later, is that this has a local excitation and long range inhibition, which allows us to do what we are about to do with this proposed particular partition. Additionally, just for simplicity, we assume that the activation function is a Heaviside step function with some threshold U sub 0. So we are interested we see the existence of the bump as some sort of equilibrium density of the probability of the activations. And this density is time independent, characterized by the fact that it needs to be the probability of being active should be greater than 0 for when the neurons belong to some region, bounded region in the domain, or in the neural field, if we call it, if we wish. And then it should be the probability of activation should be 0 outside this region. So using the unknown result, we can say that this independence, this is the time derivative, sorry, this time independence, this equilibrium density will be reached or implies that the mapping or the mapping of the evolution law is equal to some sort of operators that work on the gradient of some surprise function or functional, some energy functional, some potential. So this is trivially true in this case because it turns out that the right-hand side of this equation is just the gradient of the Hopfield energy. And it's easy to show that in the Helmholtz decomposition of these operators, we only have a gradient flow. So the flow essentially just when the fluctuations are small, we just do follow the gradient of the Hopfield energy. There's not much there. I think it's just like at least the analogy seems to be consistent. So we can move forward to try to figure out what the particular partition should be in this case for the bomb. So again, just as a reminder, we are trying to look for or trying to look to the bomb of activity, which is a localized activation in this attractor or spatially structured network, and we are trying to treat this bomb as a particle. So following again some results from the active inference literature, we take a look at the Hessian, which is essentially the Jacobian of the map of the equations, and we find that for this particular partition, the conditions for the conditions given for its existence and the existence of the bomb map very nice to conditions that we already know for the existence of bombs from the literature, from the work from Sunichi Amari and other people. So what is this partition? So this partition is essentially, we consider internal states, all the neurons that belong to the bounded region, which is the bomb. We have some active and some Markov blanket or some proposed Markov blanket, which will be sensory and active states. I'm going to talk a little bit more about that in a bit, but they all belong to the boundary of the bomb. So all the neurons that are right at the boundary, but they don't. We define this boundary as essentially the first neuron after the bomb that is not active. And then we have an external state in which is everything that is not part of the bomb. So the conditions for conditional independence, given the Markov blanket, is that the Hessian terms that correspond to the internal and external states should be zero. And this is true in this case when the weights of the kernel is zero at the boundary. So, and when this happens, it can be shown that the bomb has to exist. This makes sense because essentially, if this neuron, if the weights were greater than one, then the activation of the function, which is essentially the integral of this kernel, should cross or will cross the threshold, and it should be on. So it should be part of the internal state, but we are assuming they are not. Additionally, we can derive also from analyzing the Hessian some additional conditions which are known from the literature. And then we conclude that the internal and external states of the bomb are conditionally independent given the boundary of the bomb as defined here. So in some sense, potentially not very general, but general enough to fit at least the definition given. Given the definitions given, the bomb behaves like a particle. So this is just a simulation. So we started with some excitation, localized excitation in the bomb. And then the bomb settles into a steady state that is characterized by a positive and some negative boundaries around the bomb. And following these conditions, well, essentially the bomb has to be stable. Okay, so now I want to talk a little bit about what is this environment, the medium in which the bomb exists. And I just want to talk, just bring about a new approximation, a new limit that is used often in the literature for these networks. So if you look at the original network, we are talking, we are working on a discrete domain. So each neuron is belongs to some specific position. But if we take the limit of the uh, limit in which the domain becomes continuous, then we can describe the neural network, this ring network, as a neural field. So it's essentially the same, it just becomes a partial integral differential equation. Again, I made a mistake here. This should be the time derivative. And it is known that and in this type X, for example, could represent already some continuous variable, which is commonly assumed in the ring attractor literature to be the angle. And then this domain is essentially the circle, the one-dimensional circle. So for this network, when you have fluctuation, it is known that unless you have some particular input here that generates some drift, the bomb behaves as essentially as diffusing or as random walks. So the centroid of the bomb will perform a random walk in this domain, but it will be centered around the localized activity. We're going to ignore the fluctuations for now. We are trying to look more into that part to see if we can use all the theoretical machinery of active inference even more in this context. But for now, we're gonna just talk about the deterministic equation. And this is somehow justified because we can formally assume that this activity uh, is represents the evolution law of some sort of probability distribution of firing on the network. So obviously there should be some sort of conservation of probability mass added somehow for this to be completely true. But in that sense, having a deterministic equation is not too bad and leads to actually results that we can bring back to the spiking neural network. So I said I was going to describe a little bit the medium. So the medium that this neural network represents is a medium that supports a pattern formation. So it's a spatially structured network, and you can see the pattern formation happening when if you replace the input. Again, I made a mistake here. It's t. So if you replace the solution for an ansatz that is composed of a spatially uniform state, which will be the state that essentially has nothing in it, and some sort of perturbation that is very small but is spatially dependent. You can describe that perturbation by the Fourier modes in the space and some sort of exponential decay in time. So you're assuming essentially that the perturbation will either grow exponentially or die down exponentially, or just in the specific case when lambda is 0 will stay in the medium. So by replacing this into the original equation, we achieve this dispersion relation, which will tell us essentially the scale of the main mode of a pattern formation in the network. So you can see it here for different values, for different choices of the parameters. So in this case, we have a localized activity again starting, but then because of this pattern formation scale, it's split into multiple bomb-like kind of wave packet um, yes, phenomena, spatial phenomena. But then this one is obviously growing out of control, so it means that the lambda is greater than 0. On the other hand, we have here one that is stable, so for lambda equals 0, you just get this kind of oscillatory path. So the medium the medium of the bump is a medium in which things can happen, depending of what the inputs are and what the parameters of the network are. So we want to control the bump, and we want to add a little bit more, because right now it's essentially not very interesting. It's a particle that just exists, so I don't think it can even be said to be doing any sort of self-evidencing or anything interesting. But then we wanted to do something interesting, and the way we are exploring to do that is using gain modulation. The way gain modulation can influence the bump and can be shown using this simple exercise. So let's assume that we have a linear network. So this is the activation function. This is the composition operator, and this will be a linear network, but it will have some field of gains. So this activation function won't be homogeneous. So if you have an heterogeneous gain in the neural field, which means that each neuron responds with a different slope yes, yeah, the firing rate essentially is the result of a different linear function for each position. And then if additionally we split this gain, heterogeneous gain, into two components, one constant and one which we'll call the potential. And then we make another assumption. Instead of using the Mexican hat, we use this one. It's just for convenience. Then we can see that this equilibrium states, or the equilibrium distribution, the bump, must satisfy this integral equation. So the reason we chose this kernel here is, so this kernel in itself cannot support bumps because you don't have any inhibition. But it is very nice because it has a really nice Fourier transform. So if we apply the Fourier transform of both sides of this network, and then we reorganize and compute the inverse Fourier transform, we can get something that looks like the time-independent Schrödinger equation. And this is a happy coincidence, or because in this case we can use some analysis that people use with the Schrödinger equation to study the effect of different potential shapes or different gain distributions into the effects, into the dynamics of the network, and ultimately in the existence of a bump. So I'm just going to show the results for what is called the well potential. So if we put a gain distribution that has a low, it has, I don't know if I can write something. Here, yes, I can write. So if we uh, choose this potential function, this gain heterogeneity, as having a low gain outside the well and high gain inside some particular region, we can show analytically actually that the bump has to exist, and it has essentially just one mode, one Fourier mode that allows the existence of the bump. So in the traditional Schrödinger analysis, you find multiple energies in which the bump or the particle can exist in this well, but for this simple neural field, you only find one. And then you can even build the analytical solution by finding some consistency equations. So you just uh, set up the conditions of the solution so that they are smooth and differentiable in these corners, and then you can find exactly the bump solution, and this only happens for one specific mode. So we can use gain to control the bump on to somehow uh, change the information that is available to the bump in the environment. I hope I am not pushing the analogy too much. So now we're gonna go to to the second part, which is putting all this observation together into network that more or less um, we believe supports something like an autonomous representation that can be controlled, and it will essentially move or act on the environment depending of changes on that environment. So let me introduce this network. So this is a ring attractor. It's just unfolded. So it's the same spatial structure network with periodic conditions. We added the main medium for the neural field in the middle. And then we have these gain modulation neurons, which are tuned to essentially change the excitability of, of the network of the neuron they are they are connected to. As you can see, these neurons go in two directions, and they are influenced by two important inputs which call homeostatic units. Essentially, so these units will tell the network whether to move left or right. So if you imagine the bump here, um, so this bump will have the capacity of acting on this network through this once the conditions are right, and essentially we receive some input from this network if something happens here, and same in the other direction. Um, so this we call this homeostatic units because this is a homostat. It's a neural circuit that is found in in mammals and also in some insects for thermoregulation. So it's called the Hamel model. So what happens is that you have some sort of reference signal coming in to this network, and then you have some sort of feedback from your body, or in this case, from the internal representation. So the ring itself is connecting here. And essentially you direct opposite effects on the particular environment that these neurons are connected to. So if they are connected to the body, it will cause, for example, shivering when you are cold, or it will cause sweating when you are hot. And then this particular pattern of connectivity of this opposing reaction is seen also a lot at different scale, different levels of organization in the brain. You see it in the motivational systems in the hypothalamus, where you have approach and avoid neurons that also work in this opposite manner. And essentially, we find it a really useful connectivity pattern to control the bump. So as you mm, potentially already anticipate, the bump will move to adapt the 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 imbalances between these two inputs. So now we have a slightly more complicated network, but it's not that complicated. So we are still studying this network a little bit, but we can get some interesting results. So first of all, the network itself has, if we take the conditional independencies and the Hessian matrix view, it has already like a natural particular partition, which comes from this homeostatic pattern of connectivity. But in addition, you can show that this network can also move the bomb at a particular speed. And you can study the speed of the movement of the bomb, and you can also adapt the, the parameters so that you get some particular properties of the movement of the bomb. So um, uh, I didn't add that because I'm not 100% sure, but essentially the analogy I would like to make here is that seeing this as some sort of uh, field or electric field of kind of potential, and then seeing the bomb itself as sensing and acting on the environment by moving or essentially occupying different states of the environment. Um, so something that you can do here is because you have um, these very close connections in the continuous model, so you can tailor expand this. You can divide the network into two time scales because the gain modulation neurons in the spike inversion, they are supposed to be really fast. And they also have higher order correlations, so it's a little bit tricky to really model. So right now we are modeling using some interactions because the idea is that they have to be active only when the right homeostatic drive is active. And then you can, if you work in the fast time scale, then you can replace this here, and you can find some sort of transport equation for the centroid of the bomb, which essentially will tell you how fast the bomb moves, given some sort of homeostatic input. Additionally, something that is important here is that the homeostatic input needs to have some sort of readout or some access to the state of the bomb. In this particular case, we are using as a readout the expected value of the bomb, which is essentially the centroid. But we can obviously use different readouts. I will show you another example in a bit. So this is the result of the mean field simulation. So essentially, if maybe I show you the homeostatic drives. So initially, you have a large discrepancy between the the homeostatic inputs, but eventually they should come together, and this means that the bomb will move as long as there is a discrepancy, and then it will stop. So this is how the bomb profile looks. So it's what the connectivity pattern that we establish with the gain modulation does in practice is just to introduce an asymmetry into the synaptic kernel, and then that's what moves the bomb. All right, so this is our working horse for the moment. So now we want to show you some applications. So the first one is that this works very nice, even nicer in in spiky neural networks than in the mean field approximation. That means that probably our mean field approximation has some higher order contributions or some assumptions that we are not considering. In this case, we are inputting time varying uh, uh, continuous input to the homeostatic neurons, and then you see that the network essentially has these periods of stopping moving when it reaches the balance, and if it moves again, then it tracks the external input. And these are spikes. So this is the spike in raster. Um, so maybe so a little bit about the simulation. So it's just normal leak integrated and fire neurons with alpha synapses, and there is nothing strange. We use this network to also to represent numbers in a task that uh, intended to reproduce the phenomenon or the yeah so the phenomenon of having a number sense. um, I forgot what's the name, but yes. So it's Suvitising, right? So it's this idea that uh, when you see a number, you immediately know what number is. So we divided the bump into regions. In this case, for example, we are using a different readout, a readout that only has access to some of the neurons, and then use that to encode what the number of points it sees in the environment. We compare this. I can talk a little bit more about the results. We compare this to reaction times. So essentially, the time that the bomb takes to travel to uh, for the representation to settle. We take it as a reaction time, and so yeah, we see this is an interesting view of perception, because then you are aligning your internal representation with the external input. So here we show some other results. So there should be a particular tuning of the gain modulation neurons, which essentially justifies this nonlinear interaction term with the homeostatic neurons. And then these are just two examples for two different numbers. And then here we plot the centroid of the bump and the speed. So all these profiles can be analyzed in the Milne field representation. All right, now to finish, I might be talking too much. We also want, as we said at the beginning, to control robots using this kind of representations. And there has been a lot of work recently of using ring attractors and multiple rings to generate uh, quite a wide variety of representations that are not limited to head directions or to one-dimensional, but they can actually represent or generate grid-like or some other spatial configurations or representations. So we have created, we are testing this particular network, which essentially the goal is to separate the process of proprioception from the process of motor representations. And then in this kind of architecture, you will have a belief about what your state is that will be encoded by one of these circuits. So essentially, it's like making an observation of your body and then trying to figure out what you're doing. And then you use those beliefs to essentially update some sort of representation of action that will be ultimately used to control the joints, but also as an efference copy to control or to update the representations, generate some sort of surprise signal if something doesn't go right. So this kind of we hope for this to generate like a more natural way of having body ownership and kind of creating a control architecture that has some sort of self-representation hardwired. So we did some tests. In particular, I am talking as we, but this has been mostly the work of Ong. Um, so so this essentially Ong set up this robot, which is an ICOP simulator, and we use this proprioception to help the robot understand the head direction, but also we use it to send motor commands based on those beliefs about what the state of the body is right now. All right, so this is obviously a work in progress, as we said. Um, but we want to try to push this idea of autonomous representations, or having the representations themselves having some sort of autonomy and existence. We want to try to push it further and see what kind of consequences we can derive of this, in particular using all the machinery that has been developed for dealing with this machinery that we are obviously just still understanding. Um, it's very interesting that if you have an active inference agent, you can use that agent as a representation of something else that's happening outside. And in this case, we have at least 3 levels of active inference that are that come from the own potential self-evidencing or existence of the bomb as a particle, as a self-sustaining activity that and goes towards the sort of connections that we can achieve with this homeostatic circuit that could minimize errors given some particular representations of external variables. And then this, we believe, is also a promising direction for neuromorphic computing, because even though they don't satisfy the usual tenet of having a cheap, energy efficient a way of computing, we believe that they have to have some benefit, because obviously they are widespread in animals. And we believe that this benefit is related to the amount of information that these things can process at the same time, by essentially having an already active region that you can modify and control within the network, and localized, right? So you won't be involved in all the neurons. All right, so this work, as I say, is mostly done by the PhD student Ong Eisted, so he is on the call if you want to ask any questions. We also worked with Sarah Hamburg. This project, we worked the 3 of us together, and essentially we continue collaborating into making it more usable, at least in the area of robotics, and also exploring all these theoretical consequences that it could lead. And it has been done obviously under the direction of the group lead, which is Alessandro Di Novo, and Professor Tony Prescott, which is now working on these self-representations with us. All right, thank you very much.
Thank you, Alejandro.
Thank you.
Okay, we'll now open up for questions. So, does anybody have any questions? Please feel free to unmute yourself. Andreas?
Yes, Alejandro and Ong and Sarah, I really appreciate getting to learn about your work. I could only understand parts of it, but I felt that I should want to understand more. But I was very intrigued about the Schrodinger equation appearing. And I've thought a lot about solutions to the Schrodinger equation. And I just wanted to see, because they can be understood combinatorially. And I think that that would be very relevant for what you're doing. Usually, and so you considered a toy example where you have these infinite walls, I think, right? But a typical example would be like the harmonic oscillator, right? And so when you have a solution, you'll get an infinite family of solutions. In the case of a harmonic oscillator, they have 2 parts. You'll have a Hermite orthogonal polynomial, right? And then you'll have the square root of, an eigenfunction or whatever they call it. Well, that's a very strange way to decompose it. So I have a PhD in algebraic combinatorics. The natural way to, first of all, the natural way to think about it is that those orthogonal polynomials are encoding information about combinatorial objects, right? So that's very interesting. What are they encoding? The second thing is that why are we taking the square root of this thing? It doesn't make sense. It makes a lot more sense to have a weight function, you see. So you separate these two facts. Instead of taking the square root of everything, which physicists do for convenience, you say, no, no, that's a space-time wrapper. That's a weight function that you include when you integrate, right? So the information part is the orthogonal polynomial. The other part is part of the integral. It shouldn't be. So the first thing is that it's just very strange. Why are physicists doing this? And the reason is because I think the reason is because they think nature is stupid. Okay. When you see these Hermite polynomials, it means nature has something to say. Nature is communicating. But that's not how physicists think. They think that they came up with the math, that that's there. So what do they say? The Hermite polynomials, it turns out they're counting involutions. Okay. So and you have to look at the polynomials, and you'll see that some things are like fixed points, so there'll be dots, I think maybe like x's, and something will be basically the ways that you can pair links, okay? So like with an evolution, some things are fixed points, some things are going back and forth. It's counting that. Now, the first thing to realize is that it's the exact same combinatorics as Wick's theorem in quantum field theory. I don't know if you're familiar with quantum field theory.
I'm not familiar with it.
Yeah. So in Feynman diagrams of order, like when they have to reorganize everything, they have these operators, they have to reorganize them. So they use the exact same combinatorics. So the problem with Schrodinger's equation is that it's not really quite real, because it's not relativistic. But the combinatoric seems to carry over. So the things that I'll say will lift over. Now, if you look, okay, what's the general situation? See, you used a toy model. The same things will hold. But if you look at what are real cases, like the hydrogen atom is a Laguerre case, etc., it looks like all the real cases are Sheffer polynomials. Okay? Now, Sheffer polynomials means that when you have a generating function and you have all those infinite possibilities and you code them together, you say, okay, let's say these are p sub n of x and then t to the n, and you get this big thing. A Sheffer polynomial insists that when you have this huge generating function, it's going to look at like something like a of t times e to the x u of t. So you've got this exponential. What that means combinatorially is that you're basically dealing with partitions of space. You see, so you're constructing combinatorial space, these like ways of partitioning things, etc. So the idea, one idea in quantum physics, and I don't know what it would mean in the brain, let's say, but in quantum physics, it means that if you have an additional constraint and say the solutions have to be these Sheffer polynomials, then you get space for free, this kind of notion of space for free. Then you also, for free, you get a classification into 5 types. Okay, so and these classifications, the reason you have 5 types is because of the quadratic equation. It's because an orthogonal polynomial has to satisfy a recurrence relation, okay, between 3 different things. And it basically means like tomorrow depends on today, but it also depends on yesterday. You have 2 inputs. So you get a double causality, which I think for active inference may be interesting. You get a double causality. And what does that mean, that double causality? It means that in these 5 zones, it's a metaphysical thing. It means there's 2 directions to time. Every effect looking backwards has had its cause. Okay, that would be, I think, a passive inference. You can always look back as a frequentist and say, okay, this happened. There's reasons why. But what active inference says, what forward-looking Bayesian statistics says is that not every cause has had its effects looking forward. You see, looking backward, every effect has had its cause, but not every cause has had its effect. You get 2 directions, and you have a critical point where, like the present or a boundary, where you can switch. Okay.
Yeah.
So what it means in quantum physics, it's just strange how it all fits. But when you have this quadratic equation, you get 2 roots, A and B. And so there's 5 cases. The general case would be the Meixner polynomials.
Mhm.
And basically, what the A and B are, they're the step sizes for two different grids. So imagine in your situation, you don't have a single grid, but you have communication between two grids. Okay. And the difference is if the solutions are two real numbers, A and B, as you would typically have for a quadratic equation, right?
Mhm.
Then you're going to have a grid difference of A minus B, and the whole system is moving. Okay. So that in quantum physics, that would be called the freely asymptotically free situation where like this is all about a particle interaction. So imagine,
Yeah.
like you could imagine too, in your case, what does it
Mhm.
mean to have two particles interacting? So there's five zones. The first
Mhm.
is that they're so far away that they have no effect on each other by Heisenberg's uncertainty principle. Then all of a sudden they have effect. They enter. Okay. So you can have a combination A and zero. Zero is a degenerate root. Okay.
Mhm.
So this is like the creation of the wave function. Okay. That it's actually must be created at a certain point.
Yeah.
Then, and it's like you have two clocks and one's been reset. So you have two clocks A and B, like the particle
Mhm.
clocks. Now they're both, one is A and zero. Then the third zone is like A and A. That'd be like the bound state, like a hydrogen atom.
Mhm.
So that's A and A. And then they both collapse to zero. That's the case that we have with the quantum harmonic oscillator, you see? And then they become entangled, A and A bar, because you can have two complex roots be the solution to a quadratic equation. Now they're entangled, but they're asymptotically free entangled. So these are very five zones. They do the same metaphysics that I'm saying. And maybe just to conclude, the combinatorics has all been worked out. And what do you get? Instead of those involutions, of course, it gets more complicated, but you get uh, trees, like causal trees, with links and kinks. So you get the direct causality, and then you get a two-step causality. Okay, and
Okay.
these are called Kim's and trees. So, and maybe the last thing to say is that you see, so you get a combinatorial version of the you can do all of Schrodinger's equation with a combinatorial version because the most general case is combinatorial, and the whole system is moving with steps A, B. And that's discrete. These are discrete. See, now, what happens though in the degenerate cases is that you get A minus B is zero. Let's say like A equals B or zero equals zero. You get that thing. And then you see the system's not moving. If it's not moving, you get continuity. So it's very interesting that the continuous case is degenerate and it happens when your system is not moving anymore.
It's
And so it
continuity of space.
Yeah, you get when your system's moving, everything's discrete and you can
Yeah.
calculate it. But
Mhm.
if you have the quantum harmonic oscillator, if you have, let's say, a zero equals zero, or if you have the Laguerre polynomial case, the two frames are having the same grid size. So A minus B becomes A minus A, which is zero. So it's not moving anywhere. If it's not moving everywhere, instead of moving, it's smearing, it's becoming continuously smooth.
Okay.
So it's very curious that the continuous case is the degenerate version of the discrete
Discrete.
case.
Yeah.
So you can see there's a
Ah.
very rich thing, and I just think that I didn't understand, 80% of what you were talking about. Maybe you
Oh,
can't understand 80% of what I'm talking about, but the point
yeah.
is that if you manage to tap into the Schrodinger equation, you manage to tap into all of this metaphysics. And so the kind of maybe the conclusion is that when you talk about a particle, think about particle interactions.
Mhm.
Think about the five zones in these particle interactions, right? Think about these two types of causality. That's all very much possible because of what you're doing.
Yeah, yeah. So part of the also what we been thinking about, like maybe like a not very explicit goal, but an implicit goal of what we are doing is has been driven by this Schrodinger.
Hmm.
This I think it's a happy coincidence because it's just a very particular kernel, and you only find the time independent Schrodinger equation. But essentially, like we would like to set up uh, a network or a system that could lead to to push this analogy even further, right? So to try
Hmm.
to have like a complete Schrodinger equation, and we have even doing like Ong has been doing some experiments of making two of these bombs interact, maybe collide, maybe see.
Mm-hmm.
Right now, obviously, it's very simple, but I do think like if we find a better approximation or a better emergence of way to bring the full Schrodinger equation into our model,
Mm-hmm.
we will be very happy to explore this. And I'm particularly like very fond of these combinatorial approaches because I think they are really like a low key following all these combinatorial approaches to physics, and it will be very interesting to use them. I wonder if these multiple Hermite polynomials will describe like different scales of like or scales of interactions
Well, typically you have an infinite family, so like, and you have this infinite family, and they're basically energy levels, and the more energy you have, the more ups and downs you have, right? And then they build in combinations of these. And so the way the orthogonality works is that they all have to be orthogonal. Um,
Hmm.
and the relationship would be, it's like a ladder. So the level n depends on the level n minus 1, but also the level n minus 2. And there's reasons for that. And so you're kind of like climbing this ladder, and
Yeah.
they all work like that. So,
Yeah, in this simple example, we use the usual analysis of the hydrogen atom, and essentially what shows up is that there is only one energy, so there is only one eigenvalue. So it's
mm,
not like in the usual that you get a continuum or discrete eigenvalues. Again, because I think it's very simple, but
mhm.
seems
So
like
I'll write the three of you, and then if you like, we could talk or continue. But
absolutely, yeah.
and I'll try to learn. Then you can teach me your paper. I didn't understand.
No, you should actually. I also didn't understand much, but yeah, very interested.
Thank you.
Thanks, Andreas. Any more questions from the audience? If not, right away, perhaps I can ask Alejandro, do you guys have a way to train these ring networks? Is there some sort of optimization procedure for learning the weights in the network? Is there some sort of Hebbian learning rule? Or do you just hard code the networks and observe the dynamics after that?
Yeah, so far they are hard coded, and we are working only with gain modulation. So essentially, we just modulate the dynamics. We control the dynamic. We try to control the dynamics, but not any learning right now. We are working towards adding some sort of learning, um, but that will be future work. Yeah, I think that the usual one will be some sort of either uh, uh, synaptic plasticity, some learning rule, or some homeostatic plasticity that we could use to keep some sort of EA balance in the network.
Cool. And in terms of application, what can you help me understand compared to other recurrent neural networks or state-of-the-art generative models and so on? How might these be used in like a machine learning or robotics context? What advantage? Why couldn't some other sort of neural network learn a sort of equivalent latent space and get the same thing? What's the advantage for these sorts of networks specifically?
Yeah, so we are directly driven by applications right now. Like we want to apply this in robotics and like direct control of uh, some continuous variables like join angles in the robot, and even learning some sort of meta representations about this. But everything just based on the control of these persistent activities, which is something we are trying to figure out essentially how to do it efficiently, and it's a concept we are exploring. Uh, from the point of view of these autonomous representations or representations that can also uh, potentially choose to do something different in the neural medium, I don't still anticipate uh, any particular application apart from the theoretical interest.
Cool, thanks. That's super interesting. If there's no more questions now, then perhaps I can pass over to Carl. Okay. Yeah, looks like no more questions. So I'll hand over to you, Carl.
Thank you. Is it my turn now? Yes. Very good. Excellent. Thank you very much. Very rich presentation and very rich discussion. So I don't understand 80% of either. So we're all 80-20s. But it was certainly very enjoyable. So I'm going to just stand back and pursue Will's last question about applications and just make the point that if one takes literally having representations that have this kind of, based upon autonomous differential equations or neural field models, then you are in a position to apply this technology to autonomous behavior. And I'm thinking about simple things like walking and talking and writing, which at the end of the day must rely upon some kind of generative model that's predicated upon the dynamical systems that you've been studying that have this this autonomous aspect. Just to sort of put it in a much more classical context, systems or random dynamical systems that have either stochastic chaos or certainly a quasi-periodic aspect to them, but are also equipped with a non-equilibrium steady state and in the limit of no random fluctuations that would either have a quasi-periodic or a chaotic attractor. So you said the study of this is theoretically interesting, which I agree entirely, it absolutely is. But I would also submit at the end of the day, it probably has enormous practical implications if you wanted to make a robot that actually had autonomous behavior and could walk around. And I'm actually, I hadn't thought about this during the presentation, but I was thinking about the work of Jantani, where he basically induces these itinerant dynamics that he can then shape by basically learning as imitation to produce autonomous behavior. So you can get little robots to sort of play with a ball, for example. And I think that that would be the next generation of truly autonomous robotic control, in the sense that underneath the hood, you do have these autonomous dynamics. So that's certainly one thing I took from the presentation. The other one, again, and this is very simple-minded, I'm not going to try and reproduce Andreas's detailed deconstruction of the Schrödinger wave equation, or indeed some of your more mathematically seductive arguments, but just in a very simple-minded way. It strikes me that what you are doing is trying to use mean field approximations and possibly even neural field mean field approximations to understand analytically the conditions under which you would get chaotic itinerancy. And once you understand those, then you're going back to the spiking neural network to actually implement or realize the underlying dynamics, which you have been treating at the analytic level of a mean field approximation. That to me is intriguing. I haven't heard that approach before. Either people just work with spiking neural networks, or they just work as we do with the mean field approximations effectively. But to actually go back to the spiking neural network, that is a very interesting idea, which I think would make your approach quite unique. And then I'm asking myself, well, there's another focus here, which is this notion of bump attractors, and you framed it in terms of persistence. To my ears, that sounded more like trying to find a mean field approximation, or the conditions that would manifest a mean field approximation that showed itinerancy. because you're not interested in just persistent static bump attractors. You clearly, the whole point of the latter part of the presentation was to use your gain modulation or your Schrodinger's potentials to get them to do something interesting, like move or collide. So you're not interested in persistence. What you're interested in is itinerancy. The system moves around in a very expressive way. So there is conservation, but the conservation is just that there is a low measure pullback attractor that you can engineer. You can actually write down the certainly the mean field approximation to this manifold or this pullback attractor or attracting set that guarantees the right kind of dynamics, such that there is a persistence in the sense of a Poincare recurrence, and that you're coming back to certain parts after a very complicated journey around. And I mention that because in every simulation that we have ever done using active inference or within the active inference frame, in continuous state spaces, and also one would argue in discrete state spaces, we have always had to use this kind of itinerant attractor dynamics. There is nothing that we have done that rests upon a point attractor or simple homeostasis. It's always been starting with a generative model where you just start with this some kind of usually quasi-periodic or chaotic attractor that may or may not have random fluctuations on it. We normally use the Lorentz system, but from time to time we move to the Lotka-Volterra system, which is sometimes easier to handle if you want to have sort of chains of behavior. And just again in a very simple-minded way, it struck me that the ring attractor, just getting that sort of quasi-periodic behavior out, could be written down as a generalized Lotka-Volterra system in its mean field form. So when you're not at this stage worried about the sort of the neural field kernels and the like, you just want to write down where on your ring attractor it is. So like the R in the mean field approximation or the ring attractor work that you did. So I make that point just to reiterate. I think that focusing on the right kinds of attractors that underwrite autonomous behavior is exactly the right way to go. And if you don't do that, you're not going to get any interesting behavior. I think for you, the extra bit to the story is, yes, that's fine. I'd like to do that. But then I'm going to use what I have learned from the mean field or the population dynamics or the mean field approximation to go back to a neuronal spiking neural network and put the constraints into the lateral connectivity or the kernels and actually use a spiking neural network to realize the kind of attractor dynamics that I want to produce. So in that spirit, I was just thinking, what would be useful feedback? And there are a number of things that come to mind. I think the most generic one is the way that you would leverage active inference. At the moment, I have to say, you don't really need the free energy principle or the particular physics, derivations of particular physics or Helmholtz decompositions to do what you want to do. You just want to build a set of autonomous differential equations that may or may not be stochastic differential equations that have the right kind of dynamics, which would serve the purpose of generating autonomous behavior that can be realized in a spiking neural network and ultimately in a robotics context. So you don't even need Markov blankets. You just need to find the most generic, expressive kind of autonomous dynamics that then you can put into active inference to make it work, either realized as a spiking neural network or you're retaining the mean field approximation to produce or to realize a particular instance of this in possibly an actual robotic or virtual robotic context. In doing that, when looking at your diagram of towards the end, when you were you were trying to write down a model that had things like efference copy and generating, inferring the pose, and indeed working out the control variables for robotics. I may be wrong, but I think you've got that the wrong way round, and that you don't understand active inference, because when I saw that, it reminded me of the forward inverse formulation of control in the 1990s, the kind of thing that Daniel Wolpert and Chris Mail and colleagues were pursuing. The cerebellum of the Smith predictor, for example. Active inference doesn't need all that. All you need to do, and I'm saying this in a way to encourage you, that the application of your ideas may be simpler than you think. All you need to do is to build some autonomous dynamics and then have a mapping from this autonomous dynamics to moving some motor plant, some robotic arm. So say we wanted to move the hand around in a particular orbit to do some particular kind of writing. All you need to do is to write down a bumper tractor on a ring, and then just take the angular position of that and map it through some basis function to a point in Euclidean space that the robot is moving in, and then write down and then have reflexes, have the actuators on the robot just move in the spirit of the equilibrium point hypothesis to that attracting point. But the attracting point is now going to move as you move now to the next part of the bumper tractor. So you're pulling the arm or the finger to a succession of unstable fixed points if you're taking a sort of heteroclinic cycle perspective on the ring attractor, but which you shouldn't. But let's pretend that for the moment we can imagine that you've got a ring attractor that you've that plays the role of a stable heteroclinic channel or cycle. So you've got a succession of unstable fixed points that are visited in your dynamics. And then for each successive fixed point, you then tell the robot, or you use that as a basis of your generative model, and then that predicts what the robot should see and feel from the servos, from the proprioception, if you're a human, or from the IMUs, for example, if you're dealing with a robot. So if I was moving like this and being pulled around from this fixed point to this fixed point to this fixed point to this fixed point in a cycle, what would I expect to see? And more importantly, what would I expect to get from my inertial movement, my IMU or my proprioception? And if I've got the right kind of servos and reflexes in the periphery that will simply move or actuate the motion of the robot in order to minimize the prediction error between the actual registration of the pose or the angles and the top-down predictions supplied by ultimately what would be your spiking neural network, then it will reflexively just pursue that. So at no point do you need to infer anything. You're just you're just predicting what I want to see and let the robot realize that. Now, of course, when you articulate that in the context of active inference, there will be feedback, and there will be, if we're taking sort of a Kalman filter or predictive coding perspective on this, the generative model basically plays the role of priors the actual posterior predictions are those that have been updated by the prediction errors. So if I don't feel my arm being pulled in the right kind of circle, the right kind of orbit, and I don't see it, then I'm going to update my beliefs, and you know, I'm going to sort of slow down the movement on the bumper tractor or increase the radial velocity, for example, so that I am still tethered to the environment. I'm still inferring the environment, but crucially, the autonomous dynamics play the role of a prior that is actually constructing, scaffolding, and in fact authoring the movement of the robot. So the prediction errors, if you like, are, are just there in the service, just to ensure that synchronization or entanglement between the actual movement and that which is being predicted under these very, very precise priors that have been supplied by the by the bumper tractors that these dynamic bumper tractors that you're engineering. Let me. So I'm whittering on a little bit, but if I share my screen and just give you if I can go to the entire screen and I can share that. I don't know if you've had chance to. Are you familiar with this level of active inference? It's a bit historical now. It's over a decade old. But to my mind, this very simple approach to robotic control is going to be much more useful for you than um, any of the Helmholtz decompositions or all of that. All it's saying is, if you can build a generative model or some prior beliefs that are sufficiently expressive and has the kind of autonomy you are searching for, then you can just plug this into an active inference scheme, which just is effectively it's an extended Kalman-Bucy filter with reflexes. And that is all you need to do. And indeed, this particular example is the generative model is exactly what I just described in this example of pulling the finger around. I'm just hoping. Oh yes. So basically, So I'm assuming you haven't read this paper. Is that right?
We might have looked at it, but
A long time ago.
long ago, actually.
Right. Okay. Well, let's pretend you haven't seen it because
Yeah, okay,
I
because
think you need to demystify active inference. Active inference is much simpler. I think the challenge I think you are facing is finding the right kind of generative processes. Sorry,
yeah,
generative
yeah,
models.
yeah.
Yeah, that can be plausibly implemented on a spiking neural network. I think that's where all your heavy lifting is. Once you've done that, it's relatively simple to put it into a robot and make it work through active inference. And this is I'll try and explain why it's simple, because all you need to do is to give the generative model these priors, these dynamics, and then it sort of creates predictions in both the visual and, if you have an RGB feed, and proprioceptive or pose domains are the kind of things that you get from feedback from your motor plant or from your robotic arm, and then those predictions then generate prediction errors both in the visual domain and in the I'll call it proprioceptive because that's what I'm more used to talking about, domain. And these prediction errors just minimize variational free energy in the usual way, in the spirit of a Kalman filter. So and it's a hierarchical, so it's a Kalman filter, and it's non-linear, so it's an extended hierarchical Kalman-Bucy filter, basically.
What is the role of the reflexes there?
Right, that great question. So all we're doing is now equipping this scheme with a very simple reflex that knows the actual motor plant. So this is not part of the generative model. It's not part of the brain. This lives in my spinal cord. I have been born with this, and this reflex basically knows that. For example, if we take the biomimetic story of the classical motor reflex in an animal.
Mm-hmm.
And this is what I referred to before as the equilibrium point hypothesis. So this is from motor control in neurobiology, not engineering. So if I've got this sort of top-down prediction that has been carefully mapped to predict exactly what I would feel if I was moving in the right kind of way. So we're working in generalized quantum motion here. So we've got position, velocity, acceleration, and possibly higher order. So I got this prediction of the signals I should be receiving if I was moving in the right kind of way.
Mm-hmm.
And I've actually got my signals from, say, a stretch receptor in a muscle, an intrafusal fiber in a muscle, for example. So I got a very simple top-down prediction. And this is where your homeostasis would come in. So do you remember you were showing us the bumper tractor version of the homeostasis with the gain fields?
Yeah.
You could implement these reflexes just like this. It's just a homeostatic closed loop. And that's crucial. It's closed. It's a completely closed loop, but it's biased by these top-down predictions. But the closed loop is really simple, and all it means is that okay, I've got this top-down prediction, which is how much stretch this particular muscle or what angle this particular joint should be at. And I got a report that this is the actual angle. And I know that if the angle is too, if the angle is too big, then I'm going to reverse my motor and I'm going to reduce it. And I also know if the angle is too small, I can increase my torque and that prediction error will decrease. So all the reflex needs to know is a really, really simple mapping between, well, basically it's the derivative of this proprioception, say this joint angle, with respect to the action. And if I know the derivative of the thing being predicted with respect to the action, I can now just do a gradient descent on the prediction error or the variational free energy, which is just the accuracy, which is just a prediction error, in order to minimize the prediction error. So these reflexes are really, really simple, simply because you've been able to, if you like, map your desired states of affairs in your generative model into sensor space. And if you can map everything into sensor space, then you've got a target in sensor space. And of course, you can just use your reflexes now to minimize the error in sensor space. So all you need is the right kind of servos or actuators that just know that when the prediction, which now plays the role of a motor command, but it's not a motor command, it's just setting the set point, as it were. But it looks as if it's doing a motor command because it's causing the robot to move. But it's doing is just resetting the set point of your little homeostat.
Yeah, that's precisely the level at which we were thinking this small model that I showed at the end. It's probably I think you mentioned it better. It's a reflex. It's essentially that some command higher up sets the goal and then the system just adapts or
and that's what I meant by in physiology. That's called the equilibrium point hypothesis, where you specify the set point or the equilibrium point of your reflex, and then so if you want to move something, you just change the top down set point. And that and physiologically, that's how we work. Even to the extent we know which cells, and also you can put different gains on it, which was interesting given your homeostatic formulation in terms of gain controls. Those gain controls are probably mediated by something called gamma neurons in the spinal cord. So there's a lot known about the way that we actually work, which I'm sure you could easily reproduce in a robotics context. But once you realize that's the importance of just putting a reflex, a homeostat, an equilibrium point control on underneath the generative model, then you realize that the really difficult problem, which is the problem you've been dealing with, is how do you build these autonomous systems that send these predictions down to actually produce very expressive, complicated autonomous behavior. And in this instance, this simulated agent used a logical Volterra system just to create not a ring attractor, but a sequence of activation states that formed a cycle. And then when any one of these unstable fixed points had a high value, that basically just mapped to a point in space that then pulled the agent's finger towards that point. So that by suitably deploying these points around, I don't know if I got a, no, I don't. By suitably deploying these points, you could create very smooth, very biomimetic autonomous behavior that just traces out the orbit. So the effectively, this is a ring attractor, and that this ring attractor is to specify a sequence of points in Euclidean space, and then you just have a forward model that says, well, look, if my arm was over here, and what would I expect to feel from the joints and joint angles, and what would I expect to see? And then you get your reflexes to make the right joint angles, and of course that produces the right visual input. So if everything is working, and then you send the prediction errors up to revise your beliefs, revise your poster expectations about where you are on this attractor. So these attractor dynamics have to be very precise in relation to the prediction errors. So, but they are basically driving the movement. So on that view, is there anything more interesting? Well, you can go back and read this paper, but
yeah, absolutely.
with new eyes, you can play all sorts of interesting games in terms of the gain control of a more general sort, where it's just encoding the precision of your prediction errors in relation to the predictions that are being generated by the ring attractor. And another so just so that was action understanding and active inference. A more conversational narrative account of this, which just tries to compare and contrast different ways of thinking about implementing active inference in relation to sort of classic forward inverse control models, which are much more complicated. Is this paper here, where it sort of works through the progressive simplification that you get when you move to full to an active inference scheme, that I repeat is actually paradoxically much like how people thought motor control worked in the 1980s before the forward inverse modeling community got into the game. And I think, oh, is there an actual demonstration? No, there is not. Oh, yes, there is. Oh, so here's a prettier graphic of exactly what I was saying before. So there's a generative model that moves some invisible point around in your personal space, and the agent thinks that there's an invisible spring connecting the tip of her finger to this invisible point. So she thinks that her finger's being pulled around by this ring attractor, and then if she thinks that, she'll predict I should feel that. And as soon as she predicts I should feel that, then the reflexes make it happen. They make it real. They literally realize it. And then you can produce all sorts of interesting, I was saying before, you can play around with gain of a much simpler sort. You can actually switch off the proprioceptive, the ascending prediction errors from this reflex part. And it would look as if you equip your robot with vision, it would look as if somebody else was moving the arm because it couldn't feel the arm. And then you can get into action observation, all sorts of interesting stories. But anyway, this tells the same story, but it was written for people who were trying to think about optimal motor control from the point of view of forward inverse models and inferring what's the right command I have to give in order to make this happen, as opposed to saying make this happen when this is actually already in sensor space.
Yeah,
It's
yeah, like affordance is right, like a,
yes, yeah, absolutely. So, well, just a couple of further points here. Just let me just try to, yeah. There was one thing which I mean, I was intrigued and was impressed with the fluency with which you took us through the mean field approximations and how they unpack in this sort of neural field context and these coupled map lattices that give rise to bump attractors and all sorts of interesting things. At one point, I know for simplicity, you were talking about the limiting case of no diffusion. Um, if at some point you wanted to get into it, and one of the reasons that you might want to get into this is that to get this kind of itinerancy, you are almost explicitly invoking the solenoidal part of the Helmholtz decomposition of any flow. So we're not now talking about the probability fluxes in the free energy principle. We're just talking about any flow, any dynamics. You really want to get that solenoidal part, and I'm just wondering whether that's one of the anti-symmetric Hermitian operators or whatever that you were talking about before. But from your perspective, clearly you can write down that that solenoidal conservative, non-dissipative part that, when state dependent, just is the genesis of deterministic or stochastic chaos. Into the equations of motion. But there's another little subtle way in which you could include it if you wanted to, and that's by modeling the mean field of both under the Laplace approximation, or under the assumption that the density dynamics of your neural population have a Gaussian distribution. So if you know the functional form of your spiking neural network population, then you can describe the activity at any, say, point on a grid or a field in terms of the average and its precision or dispersion. And then what you want to do in terms of sort of building the mean field approximation to that, you would then appeal to the Fokker-Planck equation. Just to note for people listening who don't already know this, the time-independent Schrodinger equation just is the Fokker-Planck equation. So you can read that as one statement of density dynamics, provided you, as Andreas was saying, you're working with the square root of, in my case, probability distributions. In his case, it was of polynomials. But just to say that there's a beautiful connection between the Fokker-Planck formalism of the mean field approximation to your spiking neural network and the Schrodinger equation, simply because the Schrodinger equation just is another way of writing down the density dynamics in terms of the Fokker-Planck equation. So what would you apply your Fokker-Planck equation? Well, if you now have a Fokker-Planck equation of your spiking neural network with all the appropriate parameterizations in terms of the kernels and the like, then you could in principle write down your mean field approximation in terms of the actual density dynamics. It would be a Hilbert space, but you could in principle mathematically write down now the density dynamics in terms of the rate of change of the probability distribution over my spiking neural network or neural ensemble of my population. Clearly you can't do that, but what you can do is assume that the density in and of itself has a Gaussian form, which means you now just need to solve the Fokker-Planck equation, but now just in terms of its first and second order moments. And if you do that, then an interesting thing happens. The dispersion due to the diffusion now gets into the equations of motion of the mean and vice versa. So you now couple the first and the second order moments of the Fokker-Planck equation expressed in terms of the sufficient statistics of the density dynamics. And it has a it has a remarkably simple form, but I can't show you it, which is irritating. Hang on. There must be another one somewhere. Try this one. I'm very sorry. Could I if you want to pursue this, could I ask you just to sort of, there is a free PDF somewhere. I just can't find it at the moment. But all it's showing you, if you've got your equations of motion, which you have, and you've summarized the amplitude of your random fluctuations in terms of...
I can share my screen. I am looking at it now.
All right. Right.
Or maybe I can send it to the chat, maybe.
Oh yes, because this has been recorded, so perhaps we should. How did you manage to find it? Perhaps
I don't know. For some reason, my university has access to the.
Oh, I see.
This,
Well, so does mine, but I'm just not in the right place to actually. Okay, that's got a PDF, so that's quite good.
okay.
Thank you. Yes, you reminded me that we have to. Yeah, I just wanted to make it make the point that if you wanted to start exploring the effects of diffusion in the mean field via solutions of the Schrödinger wave equation or time-independent Schrödinger wave equation, or more usefully, I think, the time-dependent Fokker-Planck equation, then there is a really simple approximation afforded by the Gaussian assumption, and I think this is the key equation here, where it's really very, very simple. So the rate of change of your expectations is as exactly as you showed, just the equation of motion or the flow for any particular element of that. Plus this extra term that depends upon the curvature of the flow and crucially the second order statistics, where the second order statistics are functions of the diffusion tensors or the diffusions. So if you know your Fs, which you do, and you know the amount of diffusion you want to put into your system, which you do, you can simply couple them together. And in principle, you should be able to build your ring attractors with diffusion. Now, whether they'll have a steady state solution or not, I don't know. But at least for a period of time, you can actually integrate numerically this projecting the Fokker-Planck density onto basically basis functions. And just to come back to Andres's question, what one is doing then basically is taking a polynomial expansion of the probability density. So the expectation is the first order term, and then the quadratic term is the covariance, and then you just stop. So you're just basically casting the Fokker-Planck equation as a polynomial expansion and then truncating to second order. And then you can interpret that as saying that I'm approximating my population density with a Gaussian. Now, how would my Gaussian move around if I knew the dispersion and I knew the equations of motion of the deterministic part of my SDE? So that may or may not be interesting. The final two things were just I was just thinking, you're committed to functional forms for these expressive autonomous dynamics that can be easily installed in spiking neural networks. What's the most generic functional form at the mean field level that means you could do anything and everything? The one which I see coming up time and time again is the generalized Lotka-Volterra equation. And you see this in biology everywhere, at many, many different scales. And it just struck me that your ring attractor was if you like a sort of continuous version of this generalized form. And it struck me that, if you could write down your mechanics in a way that sort of started with a generalized Lotka-Volterra equation, that would give you the compass of things that you could do would be potentially enormous. If you wanted to leverage the what you were discussing with Andreas, the charm of weak rotation or going into complex dynamics, I have been told that the best thing is the Ginzburg-Landau equation. I don't know why, but mathematicians that I respect tell me this is the most general dynamical, functional form of autonomous dynamical systems that you can possibly get. But the problem is it is usually expressed in complex numbers, which may be good if you like quantum physics. But not if you don't. I'm just putting that out there, something that I've been told. In the sense that if at some point you could connect, instead of going from bumper tractors where you've got sort of well-behaved homogeneous lateral connections on a neural field, if you could start the other way and saying what would be the underlying kernels, which may actually be asymmetric, that would be consistent with something like a Ginzburg-Landau system, you would be able to simulate anything. There is nothing you couldn't reproduce.
All right, it's very useful,
And what was while searching for, yes, and of course then you've got this whole literature on particular variants, a special case of the generalized Lotka-Volterra, which itself will be a special case of the Ginzburg-Landau system, which is these stable heteroclinic channels, where I have colleagues, Mika Rabinovich being one of them in California, who's been selling the story that these kinds of bumper tractors on rings or stable heteroclinic channels, which are just a succession of unstable fixed points that you write down in the form of a generalized Lotka-Volterra system, are everything that you need to simulate biomimetic behavior and autonomous behavior, whether it's applied to working memory. And I noticed you were sort of doing, remembrance, quantifying the numbers, right through to walking and talking, for example. If you can sort of get it in this functional form, then in principle there is nothing you can't do. And I just came across this whilst hunting for a paper by Mika Rabinovich, and I thought this would do just to sort of make the point about stable heteroclinic channels, and noting that they have actually used this in robotics to try and elude, I presume, narrow crevices. Good.
Great. Yeah. The winnerless competition for the.
That's it. Yeah.
It's pretty cool. Yeah,
Yes,
no, that's very intriguing. Like very interesting about the relationship with the generalized Lotka-Volterra equation. And obviously, everything that you said is on point. We're definitely gonna take that on board and potentially give updates soon.
Oh, and give my very best wishes to Sarah, who I don't think is here. I see her.
Yeah,
I used to see her when she was on the Active Inference Institute's Scientific Advisory Board. And Tony Prescott I haven't seen for years. Is he one of your colleagues, is he?
Yeah, we are collaborating a lot these days. Yeah.
Brilliant. I'll give him my very best wishes.
Absolutely. Many thanks for all your feedback. That was very comprehensive.
Oh, thank you for a good presentation.
Great. Thank you, Carl. Should we have one more round of applause for the speaker?
Yeah.
Excellent. Thanks very much, Alejandro. Thank you, everyone, for coming.
Thank you, everyone.
Thank you.
Have a good rest of the day. Bye bye.
Thank you, Will. Bye bye.
See you.